going to start 4-3, which is we're going to factor quadratic equations that have special products. Specifically, what we're going to end up looking at is things that are squares. So what I want to do is I want to think about x squared minus 4. So if I were to use my, algebra tiles, I would x squared, and then I would have minus 4. Okay, so I'm going to bring out all these little tiles here, and we have x squared minus 4. Okay, so I can rearrange these 4 basically however I want, but again, I have to try to make a rectangle, right? So here, but I don't have any x terms. I only have x squared terms and 1 terms. So I have to be a little creative here. So remember, whenever, we don't have enough of these x variable tiles to fill it in, we can just go ahead and introduce a sneaky 0, right? Because x squared, or x and negative x, cancel out to 0. So I'm not really adding any new value to the equation. I'm really just adding a value of 0. So what if I put something like here? All right, so if we have that, is there any way for me to rearrange these tiles to make a rectangle? It doesn't really look like I'm able to. So let's go ahead and introduce another sneaky 0. Okay, and we're going to go ahead and then look what I have here. I've created my rectangle, but in this particular example, this happens to be what we would call a difference of squares. Okay, so this is a difference of squares, and I know this because it creates actually a perfect square where I have a length of x and 2. So let's go ahead and see that visually. Come on. I have a length of x and then 2. So this is length x and 2, and then this is length x and negative 2. Okay, and this is what it factors into. Okay, so what we're going to deal with is we are going to deal with algebraic expressions that are perfect squares, or are difference of perfect squares rather. Then what we will do is we will move on to what we have perfect square trinomials. Okay, and then from that point on, we're just going to solve some basic problems with that, and then we will move on into the next section. So let's go ahead and get started. Okay, let me zoom out a bit. Looks like I am frozen. Okay, there we go. There we go. All right, so what we're going to do is we are going to do some factoring of special products. Okay, so we're going to have 2 learning targets today, and that is that you're going to be able to, again, that same learning target 2, where we're going to solve word problems using quadratics, but then also we're going to use special products to factor and solve. Okay, so here what we have is we have to kind of understand what perfect squares are. Okay, and so perfect squares, as far as numbers go, you just have to understand, like, a square is like 4. 4 is a great example of a perfect square because 2 times 2 is 4. There's also 9. 9 would be my next perfect square because 3 times 3 is 9. So the perfect square is 9, but its root is 3. 4 is a perfect square, but its root is 2. So let's see what that looks like. So if I have a root of 1, okay, if I have a root of 1, and its perfect square would be whatever 1 times 1 is, which is 1. Okay, so what's the perfect square of 2? That would be 4, because 2 times 2 is 4. Perfect square of 3 would be 9. Perfect square of 4 would be 16. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 64. 81. 100. 121. 144. 169. 196, and then 225. Okay. So I do just kind of, to some extent, these numbers, maybe not memorized, but there should be a handful of these numbers that should be just remembered, as it makes a lot of the work that we're going to do easier. Okay, so then we also have to be able to identify any variable that's a perfect square. Okay, and so this one can be a little bit more difficult, so I'll try to go. So here, if my root is x, the square is whatever x times x is. Well, if you recall your exponent properties from 8th grade math and algebra 1, these have little 1 exponents here, and when I multiply common bases with an exponent, I would add the exponents here. So our first perfect square as a variable is just x to the second. Okay? And so then here, if I wanted to figure out the perfect square of x squared, I would have x squared times x squared, which again, I would just add the exponents to get x to the fourth. Okay, so here, x to the third times x to the third would be x to the sixth. Okay, and you may have figured out the pattern here. And x to the 12th. So as we look at this, basically any variable with with an even exponent is going to be a perfect square. And its root is going to be whatever the exponent. So the root of x to the fourth is x squared, because, 4 divided by 2 is 2, 6 divided by 3 is 3, because it splits them into these nice, little symmetrical pieces. Okay, so what we're going to do with that is we're going to have to, and the reason why I'm giving this information to you, although it's mostly review, is that we're going to need to be able to identify these perfect squares within problems that we're going to have. For example, if I want to factor x squared minus 25, this expression is very, very similar to the expression that I factored at the beginning. And it looks like my screen froze again. One moment here. Okay. And that very beginning one, the x squared minus 4. So let's go ahead and see what this looks like. So basically, the difference of squares follows this formula here. A squared minus b squared is equal to a plus b together times a minus b together. Okay, and so what you have to identify is where a and b are the roots of the expressions I have here. So what I want to do is I want to rewrite x squared as its root squared. So I got to figure out what is x squared's root. Okay, so I'm looking at the table. What is x squared's root? Well, it's x. So this is the same as x squared minus, okay, and then 25. Instead of 25, I want to rewrite that as the root of 25 squared. So let's go up here and let's see if we can find 25. Okay, and we're looking for its root. So what's the root of 25? Well, it's 5. Okay. So then now I have this rewritten in a form where I know what my a and my b value are. So x is my a value, b is 5. So then I can just kind of follow this sequence here. This is going to factor into x plus 5 or a plus b times x minus 5, a minus b. Okay. So, that's essentially how these problems are done. When the a value is 1, you can still think of this as, hey, what multiplies to negative 25 but adds to 0? Because there's no x term, so that means our b value is 0. So what two numbers multiply to negative 25 but add to 0? Well, it's 5 and negative 5. Okay, let's move on to 2. Okay, so 2 does not have an a value of 1, it has an a value of 9. So I want to look at 9 and 121 and ask myself whether or not these values have a greatest common factor, because that's what we want to look at basically every single time. This particular one does not have a greatest common factor. Okay. So what I'm going to do is I am going to look at this and try to identify, is this first term a perfect square? And is the second term a perfect square? Because this previous one was kind of easy. It was just x squared. So I think we all know x is going to be a perfect square. But what about 9? So we know x is a perfect square, and its root is x. Now we have to just check if 9 is a perfect square, and it is. It is a perfect square, and its root is 3. So if the root of x squared is x, and the root of 9 is 3, that means the root of 9x squared would be 3x. And then minus 121. 121, we have to check to see if that is a perfect square. 121 is indeed a perfect square, and its root is 11. Okay, and so now I have my a value, and I have my b value, and I can go ahead and just follow this formula. A minus or plus b times a minus b. So a plus b times a minus b. And that's the factor form. That's a 3x there, just a little sloppy. Okay, what I want you to do is pause the video and try a and b all on your own. Okay, so I'm assuming that you've already tried these. You're just here to see how you did. So the root of x squared is x. The root of 81 is 9. So that means this factors into x plus 9 times x minus 9. Okay, b, the root of 36x squared is 6x. And the root of 169 is 13. So this is going to factor into 6x plus 13 times 6x minus 13. Okay. All right. And this is what we call a difference of squares. And it's called a difference of the squares quite literally because difference, subtraction, squares, perfect squares. So whenever you are subtracting two perfect squares, x squared is a perfect square, 81 is a perfect square, it will always follow this factorial pattern. Okay. Now what I want to do is I want to go over a perfect square trinomial. Okay, so perfect square trinomials are expressions that factor, and they turn out to be literally a perfect square. The same length on the length, same length on the width as well. And they follow a pretty distinct pattern where once you figure out what your a and your b value is, it will go ahead and follow this pattern. So when your first term is a perfect square and your third term is a perfect square, if your middle term is equal to 2 times the root of the first times the root of the second, it is going to be a perfect square trinomial. And I would like to go ahead and discover this here. So let's say I have x squared plus, here I had one determined for us, x squared plus 9. 3, 4, 5, 6, 7, 8, 9, 2, 3, 4, 5, 6. So let's say I have this information that they give me in an equation or an expression that they're asking me to factor, that they give me x squared plus 6x, 1, 2, 3, 4, 5, 6x, plus 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And they want me to factor it. So we can just go ahead and find the same pattern where we're just trying to build a rectangle. So I'm going to try it like this and see if I can fill in my, and see if I can fill in my rectangle here. Okay. So if I look here, it seems like when I split my x's into 4 and 2, that doesn't seem to quite solve my problem. So what if I move one up here? Okay, and then I would have to move all of these pieces quite right over here, and that's not going to work. So that means I think I need to start moving things down here. Okay, and here, okay. Oops, I didn't mean to grab onto all of those. Okay, but as you can see here, to create my rectangle, what ends up happening is that my first term is a perfect square, it's x squared. My third term is a perfect square also. As you can see, it creates literally a square here, square of 9. Okay, 1, 2, yeah, and there's 9 pieces here. So when your first term is a perfect square and your second term is a perfect square, you need to think about what's the root of this term and the root of this term. The root of this term is x. The root of this term is 3. So then when I actually go and figure out my sides, this is going to be x and then 3. And then this will be x and 3. All right. And so as you can see, my length and width are the same. But how can I identify this pattern if I know that these two are perfect squares? Because, you know, they are not always. If you notice that this ends up being 2 times your 2, so this is going to be 2 times the root of your first times the root of your second. Okay, so 2 times x times 3. So 2 times x is 2x times 3 is 6x. 1, 2, 3, 4, 5, 6. That ends up what is being the pattern. Is you take your side length and 2 times your first term, or the root of your first, times the root of your second. 2 times x is 2x times 3, again, is 6x. And that's how I know how many will fit here. So if you can identify that pattern, the factoring becomes quite simple. So let's look at this happen algebraically. Hopefully I can find my black pen here. I'm seeming to have misplaced it. Here it is. Okay, so here I'm looking at number 3. Number 3 ends up being my root of my first is x, and my root of my second is 8, right? These are both perfect squares. My first term and my last term is a perfect square. So I need to check. So what's the root of my first? So here I'm looking here and I'm saying a is x. That's the root of my first term. What's the root of my second term? 64. That would be 8. Okay, so now what I just need to check is, does this follow the pattern where this middle term is 2 times my first term times my last term? So I just want to ask myself, is 2 times x times 8 16x? Because if it does, then it's going to follow this very distinct pattern. So 2 times x is 2x, times 8 is 16x. Okay, knowing that, this is going to factor into my first term plus the root of my first term plus the root of my last term squared, because it will just turn into a square. Okay, there is always a backup plan. So let's say this pattern for you is difficult and you're not quite seeing it. All of these problems can be factored the exact same way that you factored anything in the past. For example, this has a 3 term. My a value is 1, so I'm just looking for numbers that multiply to 64 but add to 16. So it turns out for me that that is x plus 8 and x plus 8. Okay, but when I have the same term being multiplied by each other, that means I can really just condense this down into x plus 8 squared. Okay, and this is what we call perfect square trinomials, because the factors end up being exactly one perfect factor that ends up being squared. Okay, let's go ahead and do the next one. So here I'm going to identify my my a term, the root of that is 3x. And the root of my c term, okay, is 5. So here I'm saying that this here is, the root of this is 3x and the root of this is 25, or the root of 25 is 5. So I want to ask myself, is the middle term in this pattern 2 times the root of the first term times the root of the second term? If it follows this pattern, then it's just going to be a nice perfect square. Okay, so 2 times 3x is 6x. Okay, 6x times 5 is 30x. So that means that this indeed does follow a pattern, and that this is going to factor into 3x plus 5 squared. Okay? Again, if the pattern for you, the perfect square trinomial pattern, isn't for you, maybe it's still a little over the head, one, I would suggest just keep trying and working towards it. But if you already have other methods of factoring, those methods will apply. For example, this would use the Xbox method of factoring. So I can make a little x, and I can say 9 times 25 is 225, I believe. Let me double check that, though. 18, 225, yep. This is 225. And then this middle term would be 30. So I would be looking for the numbers that multiply to 225 and add to 30. Okay, so this would end up being 15 and 15. So then I can go ahead and put it to my box here. And I can go ahead and put 25 here. I can put 15x here, 15x here, and 9x here, or 9x squared here. Then I could take the greatest common factor out. The greatest common factor between 15x and 25 is 5. Greatest common factor between 15x and 25 is 5. Greatest common factor between 15x and 9x is 3x. Greatest common factor between 9x squared and 15x, again, is 3x. So this is all going to factor into 3x plus 5 times 3x plus 5, which again will condense into 3x plus 5 squared. Okay. So all your previous methods of factoring will work. It's just if you're available to identify the shortcut, that will work. Okay, let's move on to 5. 5 is the same thing, but the only difference is that middle term is negative, meaning that it factors into, instead of a plus b, it's going to be a minus b. And this works out if you think about it, because whatever this negative number is times a negative number would end up in a positive b squared. So let's go ahead and check and see if it follows the pattern. And I'm looking at this and I'm saying that this first term is gonna, is x, and the last one's root is 11. So now I just need to check, does one thing I should mention is when the middle term's negative, instead of going 2 times the root of the first times the root of the second, you're checking negative 2 times the root of the first times the root of the second. So here I would check, does negative 2 times x times 11, well, what is that? That's negative 22x. So here you can see all of my pieces fit together. So this is just going to factor into x minus 11 squared. Okay, and again, you have these other methods to factor. So if this method isn't working for you, feel free to use those other methods. Okay, so here I'm looking at this, and I identified that all three numbers have an even value, 32, 112, and 98. So I'm going to factor out a 2. So I'm going to get 16x squared minus, 112 divided by 2. Whoops. And so that'd be 50, and that would be 56. And then this would be plus 49. So again, when we take the greatest common factor out, we're really focused on this inside part here. So the root of my first term is going to be 4x, because the root of 16 is 4, the root of x squared is x, and then the root of my last term here is 7. So now I just have to check, does negative 2 times 4x times 7 equal negative 56? So let's check. Negative 2 times 4x is negative 8x. Negative 8x times 7 is negative 56x. And it looks like I did forget just to write my x right here, so I'm going to dot that in there. So this does check out, right? This squared, and then this matches up. So this is just going to factor into 4x minus 7 squared. Okay. Now, regardless of whatever method you're comfortable with, the prior methods or identifying this as a special pattern, I want you to go ahead, move forward, and try C, D, E, and F, and check it with me when you are done. Okay, so I am going to go ahead and move in. Just assume that you've already checked these. My first term is a perfect squared. Its root is x. My last term is a perfect square. Its root is 7. And if I go 2 times x times 7, or 2 times a times b, 2 times a times b, this is equal to 14x. Therefore, this factors into x plus 7 squared. Okay, next term. Okay, a value is not 1, so I check for greatest common factor, and there is none. Okay, so I'm going to check with the root of my first is 2x. The root of my last is 3. And so now I need to check, does this middle term equal 2 times the root of the first times the root of the second? Okay, 2 times 2x is 4x times 3 is 12x. Okay, so this is going to factor into 2x plus 3 squared. All right, moving on to the next one. All right, the root of my first one here is x. The root of my last one here is 13. So this middle term's negative, so I need to check, does negative 2 times the root of the first times the root of the second equal negative 26? Negative 2 times x is negative 2x. Negative 2x times 13 is negative 26x. So it is a perfect square trinomial, meaning that this is going to factor into x minus 13 squared. Okay, the last one here, f. This one has a greatest common factor, right? I'm identifying a 3 dividing into each of these numbers. So I'm going to factor a 3 out to get 4x squared minus 13 minus 12, minus 12x plus 9. And again, I want to only concern myself with what's on the inside here. The root of my first is 2x. The root of my last term is 3, so I want to check, does negative 2 times the root of my first times the root of my last term equal negative 12x? Negative 2 times 2x is negative 4x. Negative 4x times 3 is negative 12x. Meaning this is a perfect square trinomial, so this one's going to factor into 3 times 2x minus 3 squared. Okay. And then one thing I need to fix on number 6, as I realized in this problem, I forgot about this original 3 almost, and I ended up putting here. As we look at this problem here, I have this 2 being multiplied out by here, and that is part of the expression, so I need to kind of drag that one down and say it's 2 times that. Okay. Let's go ahead and move on. All of our principles of solving quadratic equations are going to hold true. Okay, they're going to hold true. So I want to always identify, or I always want to, one, identify if I have a special product. But then beyond that, when we solve, they're basically the same. You just need to have it set equal to 0. You want your a value to be 1, or not 1, positive, my bad. And then we can go ahead and go. So I'm looking at number 7, and I want to set this equal to 0 to solve. because when I have it set equal to 0, I can use the zero product property to figure out my x values that are going to make this true. So as I'm doing this, I have a couple options. I can minus 9x squared and minus 30 to get it all on the right, or I can add 25. In this situation, I would want to add 25 because then that would keep my a value positive. All right, and now it's set equal to 0. Once it's set equal to 0, I can try to factor. So I'm looking at this and I'm saying, hey, this first term is a perfect square. Its root is 3x. This last term is a perfect square. Its root is 5. So now I just need to check, does 2 times 3x times 5 equal 30x? Well, 2 times 3x is 6x. 6x times 5 is 30x. So it is. So this is going to factor into 3x plus 5 squared. All right. And so at this point, I need to solve. Okay, so we need to think about what's going to undo that square. So we've kind of had this discussion in previous sections about what's going to undo squaring, and that would be square rooting. So at this point here, I want to square root each side. All right. I'm going to finish my work up here in this corner here. So the thing that's nice is this square and square rooting are inverse operations of each other. They undo each other. Okay, so this is going to result in just 3x plus 5 is equal to 0, because the square root of 0 is 0, because that's the number multiplied by itself that gives you 0, and then I can solve. Negative 5, and then divide by 3 to get x is equal to negative 5/3. And again, I want your answer represented as a fraction, not a decimal. Okay, let's move on to the next one. Okay, the next one, it looks like I need to subtract 12 here. Subtract 12 to get 9x squared minus 16. Now this one only has 2 terms. Okay, this one only has 2 terms, so I need to check for other ways of factoring. So if you refer back to our first page, because it seems like it's been a minute, is when I have 2 terms, I want to check if it's a difference of squares. I want to check if the first term and the second term is a perfect square. So I'm going to go ahead and do that. Is the first term a perfect square? It is. Its root is 3x. Is the second term a perfect square? It is. Its root is 4. So that means this factors into 3x plus 4 times 3x minus 4. Okay. And then what I can do is I can set each, since I have 2 numbers grouped together, multiplied, set equal to 0, that means this term or this term has to be equal to 0. So I'm going to get 3x plus 4 is equal to 0, which I would subtract 4 from to get 3x equals negative 4, divide by 3, divide by 3. That means x is equal to negative 4/3. Okay, and then I have to do the same thing for the other one. 3x minus 4 is equal to 0. Add 4 to each side to get 3x is 4. And then divide by 3 to get x is equal to 4/3, positive 4/3. Okay, so right here and here are my solutions. Kind of ran out of space, no big deal. Okay, let's go ahead and I want you to pause the video. I want you to try G and H on your own. Then we'll tackle the word problem, and that will be the end of 4.3. So I'm assuming at this point you've already tried this on your own, and you're just here to see how you did. So I'm going to subtract 20x and add 25 to each side to get 4x squared minus 20x plus 25 is equal to 0. I'm identifying my a term as a perfect square. Its root is 2x squared, or 2x. And I'm identifying my b term as a perfect square, and its root is 5. So now I just need to check, does negative 2 times 2x times 5 equal negative 20x? Negative 2 times 2x is negative 4x. Negative 4x times 5 is negative 40x. Or negative 20. I misspoke. Okay. So this is indeed a perfect square trinomial, meaning that we can go ahead and factor this into 2x minus 5 squared, which is equal to 0. I'm going to undo square rooting by, or squaring by square rooting. Okay, squaring and square rooting are going to undo each other. So I am just left with 2x minus 5 is equal to 0, which then I would add 5 to each side to get 2x is equal to 5, and then divide by 2 to get x is equal to 5 halves. Okay, h. Here looks like to set equal to 0, I'm going to add 9 to each side. Okay, and then again, I am once again identifying that my first and last term are perfect squares, where my root is x and my other root is 3. So then I want to check, does negative 2 times the root of my first times the root of my third equal negative 6x, which it does. Negative 2 times x times 3 is negative 6x, meaning that this is going to factor into x minus 3 squared. To undo this square root or square, I want to square root, which means I get just x minus 3 is equal to 0 because they undo each other. Lastly, I will add 3 to get x is equal to 3. All right. Let's move on to the word problem. Every rope has a safe working load. Okay, a rope should not be used to lift a weight greater than its safe working load. The safe working load y in pounds for a rope can be found using the function y is equal to 180x squared, where x is the circumference of a rope. Okay, so I have a rope, and they're circular in nature, and how much weight a rope can hold is going to be determined by the circumference of that circle. So like the distance all the way around it. Okay. So find the diameter of a rope needed to lift an object that weighs 720 pounds. Okay, so what we can do here is we can go ahead, and we know that the y is the working load, weight in pounds. So I can go ahead and replace y with 720. All right. Okay, so now I'm looking at this, and I want to go ahead, and when I solve problems like this, I would like to take out the greatest common factor. Okay, so I want to set equal to 0. So I'm going to get 0 is equal to 180x squared minus 720. Okay, so I'm looking at this, and I'm saying there's got to be a greatest common factor there. And it turns out that that is going to be 180. So you could go ahead and do a little bit of a trial run here. X squared minus 4. All right, and so then I want to factor this part here. So here I am going to factor that, and so I'm identifying my first term as a perfect square. Actually, these ones I tend to do like this. Okay, so this is 0 equals 180 times the root of the first, which is x, minus the root of the second, which is 2, which means that this is going to factor into x plus 2 times x minus 2, which means I'm going to have two algebraic answers to this. I'm going to have x plus 2 is equal to 0, and x minus 2 is equal to 0. subtract 2, subtract 2. X is either equal to negative 2 feet or X is equal to 2 feet. Now, again, we've kind of had this discussion in most of the problems that we've had this chapter that are word problems. Distance is always a positive thing. So I know that my circumference cannot be equal to negative 2 feet. That indeed X is equal to 2 is the only realistic answer. So I know that the circumference is equal to 2 feet. But that's not the question being asked here. The question being asked is what's the diameter of a rope needed to lift an object that weighs 720 pounds. So you need to remember that the circumference of a circle is equal to the diameter times pi. Okay, so then here, luckily this is a pretty straightforward equation where we already know that our circumference is 2 feet. So then all I would need to do is solve for d, and that means divide by pi. My exact answer would be 2 over pi. But due to this being a word problem, I think we would want to divide it by 3.14. Let me get my calculator out because I cannot do that on paper easily. All right. So this will be 2 divided by 3.14. All right. Sorry, folks. Let's just go ahead and 2 divided by 3.14, which is about 0.636. So we're going to go about 0.64 feet is my diameter. All right. Otherwise, that is the end of this section. Feel free to move on to the homework, and I will see you next time for our first look into complex solutions, which will involve an imaginary unit.